off the series. And yeah, I'd like to take some time today to talk to you about alluvial channels, which I consider complex conveyors from erosional sources to depositional sinks. And before I get started, I just want to acknowledge several people who have contributed quite substantially to the material that I'll be presenting today. They include several former postdocs of mine, Mitch Darcy, Andy Wickert, Lizzie Orr, Sarah Savi, also Steffi Tofelde, a former PhD student, some colleagues of mine at the GFZ, Jens Jarowski and Hella Whitman, Fergus McNabb, a current postdoc, and Bastian Luska, who was a master's student who did a project with me during the pandemic. All right, so let's get started. So yeah, just if other people are still signing on, I'll just start off with an outline of the talk. I want to just start to talk generally about alluvial channels and how they're linked between bedrock channels and source areas and sedimentary sinks. Then I want to talk about the transfer of sediment through alluvial channels, both from a theoretical perspective, but then also from an experimental approach. And particularly, I want to focus on how channel profiles respond to changes in environmental forcing. So specifically thinking about changes in water discharge and sediment supply, and also the modification of sediment discharge signals as we go downstream. From there, I want to take a break and talk to you about some field data we've collected over the last decade or so in the Central Andes. Then I'll talk about a comparison between theory and observations, at least a qualitative comparison. And that then leads us to what comes next on this topic. Okay, so I just want to start off with the satellite image showing the Himalayan foreland. So the Tibetan plateau is over to the left and the Himalayas are flanking that. We've labeled the Brahmaputra and the Ganga rivers, and you can see outlined in black are some big alluvial megafans. Now, alluvial channels are essentially everything you see in this image, starting from the mountain front and going all the way out to the Bengal fan. More specifically, alluvial channels are channels that are fully blanketed by sediment, and they adjust the channel geometry by either depositing or remobilizing sediment. So why do we care about alluvial channels? Just generally, in this figure of population density, the black rectangle is outlining the footprint of that satellite image. And you can see that people generally don't live much on the Tibetan plateau or the Himalayas. Where most people are living is in the Himalayan foreland. Okay, so a lot of people are living in areas that are directly influenced by alluvial channels. And importantly, any changes to the geometry of alluvial channels can directly affect things like flood hazards. Okay, so this is one of the main motivations we have for better understanding the dynamics of these channels. What I'm also interested in, however, when it comes to alluvial channels, is how they might transport sediment. And that sediment might start off in source areas where changes in climate can lead to erosion, sediment mobilization, and eventually transport of that material farther downstream. And one of the questions we have is whether or not we can use sedimentary archives or geomorphic archives to reconstruct what has happened in the source areas through time. Okay, so I'm really talking about source to sink sedimentary systems. And I'd just like to take a couple minutes to talk through this nice figure made by Brian Romans to set the stage for the rest of the talk. So over on the left, we have some source area, and that can be affected by different kinds of forcing, tectonic forcing, climate forcing, even anthropogenic forcing, and that could create some signal. In this case, it's a pulse of sediment, QS, that could be sediment supply or sediment discharge, that then enters an alluvial channel. Okay, so as that sediment signal starts to move downstream, as is illustrated here, it starts to be modified. And the modification that we can see is that the amplitude is starting to decrease. And we're also seeing a lag time developing between the peak and that forcing that we see in the sediment discharge signal relative to the onset of the forcing in the source area. So the question is, can we go to things like sedimentary archives, either in the long-term depositional sink or even along the alluvial channels, and reconstruct what happened in the source area over time? In order to do that, what we need is a very precise understanding of how these sediment discharge signals will have been modified as they move downstream. Okay, and that raises a question as well. If we're thinking about periodic changes in climate, so do these systems record signals from periodic climate forcing, given that they do seem to change signals as they move downstream? And if they do, are the signals affected by time lags and changes in amplitude? Okay, so a hypothesis that I want to put forward is that signal modification, even at relatively low frequency forcing, results directly from alluvial channel geometric adjustments, which are predictable, or maybe at least partly predictable. So I really like this figure. There's a lot of, intuitive, sense to this idea that the sediment signal is kind of diffusing as it's moving downstream. But in reality, there are a number of different ways that sediment discharge signals may be modified. And to understand those, we really need to think about the dynamics of alluvial channels. And one of the most important things we need to keep in mind is that the slope of an alluvial channel tends to scale with this ratio of the sediment supply or sediment discharge, QS, divided by the water discharge, QW. And these panels on the left just illustrate this dynamic. So in the panels, we're plotting elevation versus downstream distance. And if we start off with a channel that's graded, that's this gray channel, and we're then to increase the sediment supply but hold the water discharge constant, the slope will want to increase. And the way the channel achieves that is that it deposits sediment, so it starts to aggrade. Conversely, if we again start with our graded channel in gray, and we're to double water discharge but hold sediment supply constant, the slope will want to decrease, and the channel achieves that through incision. Okay, so these changes in the channel bed elevation can be recorded in the form of geomorphic landforms, so specifically distinct alluvial-fan lobes close to the mountain front. But as we start to go farther downstream, they can be recorded as cut and fill terrace sequences. Okay, but this aggradation and incision of the channel also affects any sediment discharge signals that are moving downstream. Okay, so just to illustrate what happens. So first of all, if we have aggradation within the transfer zone, so if it's filling up with sediment, then any sediment discharge signal that's moving downstream should decrease its amplitude, simply because part of the sediment is being locked up along the channel. Conversely, if the channel is graded, in theory, that signal could move downstream without being changed. And finally, if there's incision in the transfer zone, this is remobilizing extra sediment from along the channel. And this could cause that signal to be amplified as it moves downstream. Okay, so a critical point here is that any transient adjustment to that alluvial channel profile will result in either damping or amplification of that QS signal. Okay, so this is theoretical in a way, very simple, but theoretical. The question is, do we actually see this? And one of the easiest ways to test that is to start off with an experimental setting. And this is really based on work that Steffi Tofelde did as part of her PhD. She went to St. Anthony Falls lab to work with Andy Wickert and Sarah Savi. You can see Sarah in the upper left corner there. And you can also see a picture of their setup. So there's a single inlet in which they're adding water and sediment, so QS in and QW. It then flows down through this tank that's filled with sand, and then there's an outlet where they can measure the sediment coming out of that system. They can also do high-resolution scans at different points in the experiments, such that they can create these detailed little digital elevation models in which you can see some nice little terraces developed along this experimental channel. So I'll just walk you through some of Steffi's results to start with. So the first panel is showing some control experiments, so there are no changes in the forcing. And what you see in the top panel is that the water supply, QW, is held constant, and so is the sediment supply in orange. The next panel is showing how that channel slope is changing. So there's an initial phase that's shown in gray where the channel is just finding its steady graded form. After then, there's really no change. You can see that the average channel width is bouncing around a little bit, no big changes. And finally, we can see that after the channel has adjusted, the sediment coming out of the system is roughly equal to the sediment coming into the system. So sediment coming in is from the orange line, and sediment out is in these gray circles. You see two different color circles because they're two different control experiments. Okay, so this just gives us a sense of the overall variability in the control experiment. So next I'll talk you through the first experiment in which Steffi induced some change. So after the channel has adjusted itself, she increased the water discharge. What you see then is an immediate decrease in the slope of the channel. Also an immediate decrease in the channel width, that's shown in green. And behind that in gray is one of the control experiments, just for reference. And at the same time that the slope is decreasing and the channel width is decreasing, we see a big spike in the amount of sediment coming out of the experiment, right? Far exceeding the sediment coming into the experiment. So what we think we see here is a nice illustration of this lowermost scenario where we're getting incision into the channel that is then causing amplification of that signal, that QS signal that is coming out at the outlet. Okay, in the next experiment, Sheffy decreased the water discharge and we see exactly the opposite behavior. Okay, so we see that the channel slope increases. Also, the average channel width increases. And although it's a little hard to pick out, the sediment coming out of the system is actually slightly lower than the amount of sediment that's being added to the top. Okay, so what we think we're seeing here is an illustration of this uppermost scenario where the amplification, where there's damping of that amplitude of the signal. Okay, so here's just a little summary figure. What I just talked you through is shown in the left panel. Steffi also tested what happens if you change the incoming sediment supply. I'll just briefly talk you through that. So first, the dark orange line is showing when she decreased the sediment supply. Okay, that resulted in scission of the channel. Interestingly, however, at the outlet, we see no change in the sediment output until the channel has fully adjusted and the sediment coming out of the system equals the amount of sediment coming into the system. Conversely, when she increased the sediment supply to the channel, she saw aggradation, the slope increased. Again, there was no change in the amount of sediment coming out at the outlet until the channel had fully adjusted, and then we see that the sediment leaving the system equals the sediment entering the system. Okay, so just a little summary on the right. So any changes in water discharge at the inlet lead to transient changes in sediment discharge at the outlet while the channel is adjusting. Conversely, changes in sediment supply are strongly damped while the channel is adjusting. And changes in the sediment discharge at the outlet only occur after the channel has adjusted. Okay, so we're seeing quite some different behaviors here, but a critical thing is to really understand the time scale of that channel adjustment, all right? So that leads to the next obvious question, well, over what time scales do those channel adjustments occur? I'm not actually going to answer that question yet. We'll get back to that. What I'd like to do next is actually talk about some field data. So I'll be talking about a number of different results that we've collected over the last decade or so from the Central Andes. It's going to be a bit of a data dump, but what I want you to keep in mind is that each site that I'm going to talk you through records one or more distinct periodicities and climate forcing. So what are we looking at? Over on the left, this is a map of the Central Andes. The colors are showing yearly rainfall. So red areas are dry, the blue areas are wet. Over on the right is topography. And I'm going to really focus on these three sites with the stars in the south because that's where my group has been working. But I'll briefly mention some results from the Western Andes in Peru as well. Okay, so before I talk to you about the field data, I just want to give you a brief primer on climate in the Central Andes. And I think it's useful to just start to think about what happens on an annual basis. So during the austral winter, a lot of the rainfall is focused along the intertropical convergence zone, which tends to lie to the north in the northern Andes. During the austral summer, however, the South American monsoon system tends to draw that ITCZ farther south. And also there's the development of this South American low-level jet that tends to drive more rainfall into the Central Andes. Okay, so there are two main factors we tend to think about in terms of bringing more rainfall into the Central Andes. It's shifts in the ITCZ and also the strength of the monsoon. These vary on annual timescales, but they also vary on much longer timescales as well. And particularly when there are disturbances to the North Atlantic circulation, such as through things like Heinrich events, this tends to lead to southward shifts in the ITCZ, and those occur on approximately kilo-year timescales. Also, variations in solar installation affect the strength of the monsoon system, and those occur on timescales of tens of thousands to hundreds of thousands of years. Okay, and just to remind you what we're talking about, these variations in solar insolation are related to the Milankovitch cycles, and these include approximately 20,000-year precessional cycles, 40,000-year obliquity cycles, and 100,000-year eccentricity cycles. Mention that because you're going to hear those numbers again, okay, once we get to the field results. So as I mentioned, I'm going to focus on 3 sites where my group has been working over the last several years: Toro Basin, Humahuaca Basin, and Campo Arenal. So I'd like to start with Campo Arenal. This is where Mitch Darcy has done his postdoc work. There are a series of alluvial fans along the western flank of the Sierra de Aconquija. And Mitch mapped these out beautifully, and he dated a number of these different fan lobes using beryllium-10 exposure ages on boulders on those fan surfaces. So let me just jump to his results. So you can see his results up on the top. They're individual boulder ages at the very top of this plot. You could see in these cumulative PDFs, ages that he's associated with individual fan lobes. So each lobe has a different color. And what Mitch has also shown below is his estimate for when an individual fan lobe was incised. And the idea behind this is that any given fan lobe is clearly not forming at one point in time, right? Fans are forming over a period of time. But when we're comparing these to paleoclimate record, it might be useful to have a specific point in time to use for comparison. Okay, so we could basically look at those incision times and then compare them to some paleoclimate or hydroclimate indicators that we see down below. Okay, so what we see first in this next plot is solar insolation, and we can see that 3 of these incision phases correspond to peaks in the solar insolation. The next plot is showing things including the Delta 018 record from the Batu Vera cave. This is a proxy for monsoon strength. And you could see that these peaks in solar insolation correspond with strength in monsoon phases. Interestingly, there's this other peak in the Delta 018 record that corresponds to an incision phase on the fan lobes, but it's not at a peak in precession. If we look at the precise age, we can see that this corresponds to the Younger Dryas event. Okay. The other record I want to point out down below, there are these 3 little black symbols labeled M1, M2, and M3. These are actually dated moraines from the Sierra de Aconquija, so just upstream of the alluvial fans. And we could see that these incision phases, at least in these cases, are all corresponding to the timing of a glacial advance. So all of these records are suggesting that the timing of incision of the fan lobes is associated with wetter climate phases in the past. And if we look at the cyclicity, what we see is clearly some 20,000-year cycles, but maybe also some incision phases that occur on timescales even shorter than that. So these are just the first 3 lobes. Mitch also dated some older fan lobes, which you could now see that have expanded the time axis. Once again, we could focus on those incision periods. And you could see that these incision phases tend to correspond to global glacial phases, which in the central Andes are also relatively wet. Okay, there's a single paleoclimate record from the central Andes that extends back to these timescales from Lake Titicaca. And you can see that there are peaks of saline diatoms and calcium carbonate that recur. And these are essentially corresponding to drier climate phases. Okay, so what did I just say? Here we're seeing what looks like 100,000-year cycles in terms of the incision of these older fan lobes, but we also saw 20,000-year cycles in the younger fan lobes, and maybe even some evidence for incision on shorter timescales. Okay, so next I want to go to the Toro Basin, where Steffi Tofelde did more of her PhD work. And she dated a number of these beautiful terrace surfaces using a combination of beryllium-10 depth profiles and the different terrace surfaces. She also found a couple ashes and did some beryllium-10 and aluminum-26 burial dating. So we'll jump to her results, which you can see down below. So these little blue PDFs are showing her terrace ages. You can see we've dated T2, T4, and T6. So we don't have dates for T3 and T5. But if you look at the ages of those terraces, you can see they're recurring about once every 200,000 years. So if we associate an age with these other undated terraces, we're probably looking at 100,000-year cyclicity. Okay, supporting that cyclicity is the fact that the ashes, representing a time of aggradation, occurred during the dry phases. And even though these two burial ages had very big uncertainties, the central ages are also corresponding to a dry climate phase. So just like in Mitch's alluvial fans, it seems like there's aggradation during dry climate phases and incision during wet phases. Here, however, we're only seeing 100,000-year cycles. Now, where Steffi was working is in this downstream portion of the Toro Basin. Lizzie Orr traveled a little farther upstream to a series of alluvial fans, and she's also dated those. So first of all, Lizzie found that there looks to be two generations of surfaces. There's a higher generation, which she's colored in these warmer colors. So there's brown, red, orange, and yellow, and there's a younger generation in these cooler colors. She also dated these surfaces using beryllium 10 ages on boulders. And here are the results. So the older fans are actually rather difficult to date. You see this big spread in ages on the individual boulders, but they're really old, right? So possibly we're looking at 100,000-year cyclicity, but that's not very clear. The younger surfaces, on the other hand, are quite a bit younger. And if again, we focus on the timing of incision, it looks like we're seeing, once again, approximately 20,000-year cycles. Okay, the final slide I have for the data dump is from the Humahuaca Basin and also these two sites in the Western Andes. All the dates we have available are from OSL dates or carbon-14 ages. So the Humahuaca ages are shown in orange, the Western Andes are shown in gray. And we can compare these to some paleoclimate records you see down below. What are we looking at in this case? Well, in the Humahuaca Basin, it looks like we could have 40,000-year cycles, whereas in the Western Andes, maybe again, 20,000-year precessional cycles. So where are we now? This slide is meant to summarize what I just said. In Campo Arenal, we saw several different cyclicities, 100,000-year, 20,000-year, and maybe even less than 20,000 years. In the Toro Basin, the downstream terraces showed 100,000-year cycles, whereas the upstream alluvial fans showed 20,000-year and maybe also 100,000-year cycles, whereas in the Humahuaca Basin, we saw 40,000-year cycles. So at this point, we might ask the question, why do these different field sites record different periodicities? And also, why do some sites record multiple periodicities? And to be honest, we scratched our head over this for quite some time. We're actually getting very frustrated. It felt like every time we went to a new site, we were finding something different. And this was very confusing because we went in with the assumption that all these sites are experiencing a very similar paleoclimate history. So what is going on? Well, it turns out it might not be that complicated, and we just need to think in a little bit more detail about how alluvial channels respond to cyclic forcing. Okay, and we also want to keep in mind exactly what we're looking at. All right, we're looking at these alluvial fan lobes and river terraces. So we're looking at signals of aggradation and incision along these alluvial channels. Okay, so to really understand what we're seeing, is very helpful that Andy Wickert, as part of his postdoc, developed a model for the evolution of alluvial channel profiles, and specifically these are gravel-bedded channels. So this is DZDT, and I'll just quickly step you through what is in this equation. So there's a set of constants out in front, and just briefly, there's this KQS term, which I'll explain in more detail later. There's an intermittency term. This is just telling us what proportion of the time the channel is doing geomorphically effective work. There's a sinuosity term and a porosity term. dz/dx is the channel gradient. Okay, and as we move to the right, there's a diffusive component and an advective component. And they include terms like Q, which is the water discharge, and B, which is the valley width. Okay, there's also an uplift term, which means we can impose uplift or subsidence on this whole channel system. So one thing I'll point out is that this diffusive part is actually dominant within this equation. So we have something that is actually close to a linear diffusion equation. So what do we know about linear diffusion equations? Well, the response time to any perturbation of this equation should scale with the length of the system squared divided by some diffusivity term. And as Chris Paola pointed out in 1992, we can also determine the length of the channel, so L prime, that is perturbed by any given forcing frequency. Okay, and that also scales with this diffusivity term. So without even explicitly solving for that diffusivity, we can start to think about how this system will respond to perturbations, and we can see it directly when we force this equation with periodic changes in water discharge, and that's what we're looking at here. So in the panels on the left, we're forcing the system with 4,000-year variations in water discharge, and you can see that only the uppermost portion of that channel is experiencing aggradation and incision. Conversely, if we force it with 20,000-year forcing or 40,000-year forcing, a longer portion of that channel is experiencing aggradation and incision. Okay, so this is actually completely consistent with what we saw in the field. Okay, so specifically, the forcing period is controlling how far downstream aggradation and incision extends. It's consistent with what we see in that at the upstream sites, so at the alluvial fans, where Mitch Darcy was working and where Lizzie Orr was working, the channels appear to record multiple forcing frequencies. Whereas at downstream sites, like the Humahuaca terraces, and especially the terraces in the Toro Basin, the channels only record low frequency forcing. And that's simply because that distance is filtering out that higher frequency forcing. So let's just come back to this nice figure from Brian Romans and come back to these questions I posed. So first of all, do these systems record periodic climate forcing? Well, first, in terms of geomorphic landforms, the alluvial fan lobes and the river terraces, upstream regions seem to be more likely to record high frequency forcing compared to the downstream regions. But what about sediment signals, like sediment discharge signals that might be traveling downstream and arriving at these depositional sinks? And also, what about potential time lags and changes in amplitude? Okay, I haven't said anything about that yet. And that's actually the goal of the gyroscope project. So this is a project that I had funded through an ERC consolidator grant. And you can see below the cast of characters we have working on this question. And let's just jump right into that. So something I've tried to emphasize is very important is the response time of the channel system to some perturbation. So Fergus McNabb has been working on trying to better quantify that. And quantify is still estimated, but what Fergus is looking at is this relationship. So the response of the system, we're going to relate to the length of the system squared divided by a diffusivity term. And Fergus has derived a diffusivity term based on that equation that Andy Wickert derived. Okay, so let me just point out the first term over on the left. He has described this diffusivity in terms of water discharge and the slope of the channel. But it turns out we can also interrelate water discharge, sediment supply, and slope. So we can rewrite this diffusivity term also in terms of sediment supply and slope, or in terms of sediment supply and water discharge. Okay, and I'll just point out in this last formulation that the water discharge term is actually quite a bit more important than the sediment supply term. So we think of this diffusivity and the response time of these channels as being primarily controlled by the water discharge. So what can we do with that? The other thing I've tried to point out is that the way a channel responds is also dependent on not only the response time of the system, but the forcing frequency relative to that response time. So Fergus has very nicely explored this idea. What I'm showing here are some figures he made. In the left panel, what he's looking at is a high frequency forcing of this system. So in this case, the period of the forcing is equal to that response time or equilibrium time divided by 10, right? So it's a very high frequency forcing. The middle column is showing a forcing period that is equal to that response time. And the right-hand panel is showing that the period of forcing is much longer than the response time of the channel. So this is very low frequency forcing relative to channel response time. So what do we see? In this case, Fergus is forcing the system with variations in water discharge. You could see down below what we've already illustrated in those little animated GIFs. Right? We see the channel aggrading and incising as a function of downstream distance. What's very useful about these plots is that we can also see what's happening with the sediment discharge coming out of that system. Okay, so under high frequency forcing, we could see that the sediment discharge signal, which is shown in the black line, has a very similar amplitude and is nearly in phase with the forcing. Okay, if we go to a slightly lower frequency forcing, what we see is that the amplitude of that sediment discharge signal at the outlet is actually slightly amplified, right? So it's a little bit bigger. And you can also start to pick out there's a little bit of a negative lag. And that means that the peak in the sediment discharge at the outlet slightly precedes the peak in the water discharge at the inlet. Okay, kind of weird. It gets even more weird when we go to very low frequency forcing. The amplitude of that sediment discharge signal at the outlet is now actually substantially reduced, but this negative lag time is quite big now. Okay, so that's what's happening when we force the system with changes in water discharge. We could also look at what happens when we force the system with changes in sediment supply at the inlet. Okay, so once again, the forcing is shown in this pink line, and what is happening with sediment discharge at the outlet is shown in the black line. So if we have high frequency changes in sediment supply at the inlet, we essentially see no variation at the outlet. And that means all the variations that occur at the inlet are being absorbed through channel aggradation and incision. If we go to slightly longer forcing periods, we start to see some variation in the sediment discharge at the outlet. And we can also start to see some lag time developing. Okay. And if we go to very low frequency forcing, the amplitude of that output signal is bigger, and the lag time has also decreased so that it's actually quite small. Right? So there are quite substantial variations in what we're seeing coming out of the system, that sediment discharge, whether or not we force with water discharge or sediment supply. And also critically, it depends on the forcing period of the system that we're imposing relative to the system response time. So I've actually just shown you a few snapshots of Fergus's results. In detail, he's worked together with Jens Tarewski to use an approach called perturbation analysis of this equation, this model for alluvial channel evolution. And what that allows them to do is come up with an analytical solution to that equation and quantify the gain, which is any changes in the amplitude of a signal, and also a phase shift for any distance downstream, and also any forcing period relative to the system response time. So I'll just try to explain this in a little bit more detail and not go into all the detail that I'm sure Fergus can tell you about. So this first column is showing aggradation and incision, so changes in Z. Okay, on the x-axis, we're seeing how those changes occur as a function of downstream distance. On the x-axis, we're looking at the period of forcing relative to the response time, and that's varying over 4 orders of magnitude. Okay, we can also look at, well, what happens with sediment discharge coming out of the system. We can also see that as a function of downstream distance, and we can look at what happens to the gain, right? So changes in the amplitude and also the phase shift. We can also look at what happens to that sediment discharge signal if instead of varying the sediment supply at the inlet, we vary the water supply. Okay, so there's a vast range of different behaviors here. And what's incredibly powerful about these results is that we can see what's going to happen in these channels over a vast range of parameter space. Okay, so what comes next? Fergus has done a tremendous job looking at the implications of this model. And what's particularly powerful about this model, I didn't really mention it before, is all these parameters are things that we can actually define in the field, right? The one thing that's a little bit tricky is what I've circled here, the KQS and the I term. Just remind you, the I is the intermittency. So that's the fraction of time in which the channel is doing geomorphically effective work. That might be the timing of the Bangful flood, or it might be some other time of a lower water discharge. As long as we're moving sediment, we're moving bedload, that will be included in that intermittency. The other term is KQS, and KQS actually lumps together a number of different coefficients that were related to different equations that were used in the derivation of this model. Okay, so that includes a Meyer-Petter-Mueller sediment transport equation, a Manning-Strickler grain size dependent roughness formulation, and also equilibrium channel width. Okay, so the coefficients within these equations can be defined fairly well based on experimental studies. So we can actually come up with a number of KQS based on experimental studies. The question is, can we use that same number when we're going to a field site? And we don't know. So this was one of the goals of the master's thesis of Bastian Lusk, to try to quantify that term for some field sites. So what he did in detail is he used this relationship, which I've shown here, between water discharge, sediment discharge, and channel slope. And he used this relationship in systems where we can actually define it for several different tributaries within one drainage basin. Okay, so he's plotting QW on the y-axis and QS over slope to the 7/6 on the x-axis, then fits a linear regression through it, and the slope of that line will be equal to this term 1 over KQS times I. Now, this doesn't look like a linear plot because I'll just point out it's actually a semi-log plot. Okay, so what did he find? Well, he sees that this term varies by a factor of about 2.5. So this gives us some sense for how much variability there might actually be in that term in real field sites. Obviously, this is something that can be explored in much more detail. And it might be that anytime we want to apply this to a field site, maybe we have to do a local calibration. Okay. Next point, what is the effect of different river network geometries on lag times and gains? So this is another thing that Fergus is working on at the moment. And he's using a networked version of the model that Andy Wickert has developed. Okay, so rather than having a single thread channel, we have a whole network of channels that come together. And at every inlet, we can define sediment and water supply. And you can see over on the right, the kind of behavior we're seeing. So once again, we're seeing aggradation and incision, and we can track what's happening with sediment discharge at the outlet. Okay, so ideally what Fergus is aiming for is trying to understand what kind of behavior we might see from different types of network configurations. And finally, can we test these theoretical predictions with field data? And that's really one of the goals of the other people in the project. And what we've decided to do is look at kind of two different M members of channel network geometries and see what we see, basically. So southern Patagonia is one site. The Rio Santa Cruz flows from Lago Argentino on the left, all the way out to the Atlantic Ocean. So a couple hundred kilometers with essentially no tributaries. The tributaries that are there are very small. So this could be something quite close to a single threaded channel. Conversely, if we look at the Narin River in the Kyrgyz Tien Shan, it's flowing through this region. It's a very complex network. There are a number of very large and smaller tributaries. In both systems, there's tremendous preservation of river terraces over several hundreds of kilometers. So they're excellent locations to start to look at some of the predictions of the model, and particularly how these aggradation and incision signals will evolve as we move downstream within very different network configurations. So what are the goals? Eventually, we'd like to try to predict the impact of climate forcing on channel response. That means aggradation and incision, and sediment supply to sinks for any channel network in the world for any forcing frequency. And that's probably a little overly ambitious. There probably are limits, right? So signal shredding is probably happening at higher frequency and lower amplitude of forcing. These are the kinds of processes that will just add a lot of noise that are very difficult to predict. So these could include things like bank collapse along the alluvial channel, maybe some meander cutoffs, maybe even the migration of very large bed forms. At some point, we cannot apply the model we're using to these short timescales. The question is, where exactly is that limit? And we don't yet know. And another question is, can we make direct comparisons with the stratigraphic record? So I think what became pretty clear from my talk is I'm quite focused on alluvial channels and the river terraces and alluvial-fan lobes. Of course, the next question is, can we go to a stratigraphic record and use that to also test predictions of the model? So this is not really at all included in the scope of the project at the moment, but yeah, we'd be very interested if any of you know of great sites or great records that you think would also be useful to try to test this model. So yeah, with that, thank you for your attention, and I suppose there'll be some time for questions.
Thanks a lot for this very nice talk. That's super exciting. So the chat is now open for questions. We do have time for questions. You can also raise your hand if you want to ask the question directly to Taylor. I may actually start with the questions. Just by curiosity, you presented the reactions of the model compared to upstream changes, upstream perturbations. By upstream, I mean the change of sediment supply or water supply. Have you tested at least the theoretical reaction to a downstream perturbation, like a base level fall? Does that overwrite the systems, or?
You mean if that were to happen simultaneously?
Yes, yes, yeah.
From upstream?
I'm thinking in a modeling point of view.
I haven't tried that. I don't think Fergus has tried that. Yeah, that's a good question. It's not a difficult model to use. It's all written in Python, so I guess that's one issue. It's an issue. But Andy's model is available on GitHub. So if you're reasonably comfortable with Python, it's not too difficult to just get in and change these parameters and see what happens. So yeah, but no, we haven't tried that yet.
Thanks. So we have a first question from Aggrade Larsen. Hi, Taylor, thanks a lot. This is a super fascinating talk. I was wondering if vegetation plays a role in the model, and if so, how do you implement the role?
In the model, there is no vegetation cover. We're purely just simulating what's coming into a channel and how that channel responds. Certainly, when we think about what happens in real landscapes, vegetation cover changes will be important. And I think this is one of the main factors that can lead to maybe not, coupled changes in sediment supply and water supply into your channel, but quite some changes over time. What we think is happening in the central Andes, the reason why we get these really big fills is that it is a semi-arid environment. And when that area gets wetter, a lot of sediment is removed from the hill slopes and causes massive aggradation in the channels. But in theory, if it's wet enough, we should be able to increase vegetation cover, reduce that amount of sediment that's being delivered to the channels. And this would add certainly another complexity. So, in the scope of a landscape evolution model, I think it'd be quite interesting to couple more of those dynamic hill slope processes to a model like this, which is specifically just treating what's happening along the alluvial channels and seeing what kinds of things will happen in real landscapes as we change climate.
Okay, so we have another question from Richard Ott. It says, how do you date incision periods in your field studies you showed in the beginning?
Yeah, so in terms of dating incision, what we are assuming is that the end of aggradation slightly precedes the start of incision, right? So we're not directly dating incision there. That was the case for Mitch's alluvial fans, where we have a whole series of boulders across these surfaces. And what we're just assuming is that we can use that spread in ages together with some statistics to estimate, well, what is the most likely time that we incised? When there is another fan lobe that's clearly started to form, that also can give us another constraint, right? So after the incision, we start a new fan lobe, deposition on a new fan lobe. So it gives us another indication. With the river terraces, yeah, it's again, just really dating that uppermost surface and assuming that after that long phase of aggradation, we have a stable surface. If we date that, that's going to shortly precede the incision phase. So yeah, we're not precisely dating the incision, but we're more inferring it.
Okay, we have a question from Emma Lodes. Thanks for the really interesting talk. I'm curious if you have thought about changes in tectonic uplift over the time periods you're investigating. Or is the tectonic timescale too long to have an effect?
Tectonics will definitely have an effect on these alluvial channel profiles, and it's why it's explicitly included as a term in Andy's model. There's that plus U at the end. It definitely has an effect on the shape of the river profiles, and specifically if there's subsidence happening under the alluvial channel. It basically causes it to increase its concavity. because you're kind of just pushing up the bottom and the channel just develops this very strong concavity. Conversely, if you cause it to uplift, you get a much straighter channel. So it definitely has an effect on the shape of the channel. If you cause any changes in tectonics, right, you can certainly cause nick points to migrate upstream. So yeah, I mean, the alluvial channels will certainly respond to that tectonic component as well. And yeah, I guess you need to decide for yourself if you think tectonics are stable within your area or they might be changing over time.
Cool. I've got to throw in another question. I think we haven't got any more just yet. I was wondering if with each climate perturbation you get through, are you expecting the same water or sediment kind of ratio to change in the same way with each wave, and think about kind of preconditioning of a landscape and imprinting on top of each other and what the catchment's doing and how that's driving what's going downstream.
Yeah, and I'd say none of those dynamics are included in the equation itself, right? So really it's just, yeah, what you put into the model is what you decide. So if you have some understanding of how you think that forcing will change, that's something that you can impose directly. It's something you might get some better insights for if you have more, a very detailed landscape evolution model, for example, or some very good field data, perhaps. But there's nothing in the model itself that will directly include some of those very complex kinds of feedbacks that you're discussing. Yeah.
And does it actually, because did you mention grain size there? Was it in the terms? Or it was the mobility of the sediment or something like
grain size is not in the equation. So, and that was a very clever trick that Andy Wickert did. And basically the reason why grain size is dropping out is that he's assuming this equilibrium channel width. And in some ways it's an assumption. It also kind of limits our application. So if we're just looking at how these alluvial channel profiles are evolving, the importance of grain sizes does drop out when you have an equilibrium channel width. In reality, of course, do you always have an equilibrium channel width? No, it's going to find its equilibrium over some time period. How long is that? It could be years, maybe it could be decades. So this is probably one of the things that will set the limit on how high, what kinds of frequencies we can really force this model and expect to get reasonable results, right? As we go to timescales of maybe less than a decade, we probably can't trust those results.
Okay, thank you. I'll hand over to Boris. There's some more questions in the chat now, I think.
There are more questions. So the next one is from Anne Bernard. Hi, Taylor. Thank you for this very interesting talk. For your single thread channels in Patagonia, these originate in big glacial lakes, right? Mm-hmm. How will this affect the field data you guys will collect downstream in terms of being able to test the hypothesis?
Yeah, it's a really good question. We don't know. I mean, we've thought about it a little bit. So yeah, I mean, what we see today is there is no glacier. There's this giant lake. There is water coming out of the channel, but a lot of that coarse sediment is obviously going to be trapped in the lake. And it's only when the glaciers are going to advance to the front that you're going to get maybe that coarser sediment supply and the water. So we think there could be quite strong variations in water and sediment supply in these systems. We don't know what we'll see. We actually do have some initial results, I could say. And it seems like we're seeing some 100,000 year cyclicity going back to about 1 million years within that terrace system. And they are like spectacularly preserved terraces. What we have no idea about, so the initial results are just from very far upstream. What we don't know is what's going to happen downstream, which ages will survive, which surfaces will survive. Yeah, and I think depending on how quickly the AMS in Cologne gets to our samples, we'll have an answer for you sooner. But yeah, I think this is quite exciting. A system that might show much bigger variations compared to some of the other sites we're looking at, because you have this big proglacial lake that could be trapping sediment for quite substantial portions of time.
Okay, we have a question from Luca Malatesta. Great project. The years to come will be exciting. Given the work done so far with gyroscope, what are the most challenging field constraints to obtain?
The most challenging field constraints. I mean, essentially what we're doing is trying to go and date these terraces over very long distances, right? So we're traveling big distances in the field, trying to find good sites, trying to find good material. We have a lot of samples. So far from Patagonia, things are going pretty well. The lithologies are reasonable. We have no idea if our samples from Kyrgyz Tien will work. We collected a lot of OSL samples and some boulders also for exposure dating. We just have to see what happens. Yeah, this is one of the tricky things about working in the field. Just dating surfaces seems pretty straightforward, but depending on the field site, it can actually be quite tricky. And I'd say like the other big component is really comparisons to the stratigraphic record. You know, as I mentioned, you know, there's just we have no scope to do that in the present project, but I mean, this I think would be really fascinating. So it'd be great if, you know, anyone listening to this talk or reading, you know, some of the papers that are coming out, if they're excited about this, yeah, it'd be just great if they also use this model to try to test some predictions. That'd be fantastic.
Great. Okay, so we have another question from Alec. He says, how might glacial forcings and paraglacial response of proglacial melt and sediment exhaustion fit into this picture?
It will potentially, yeah, affect the amount of sediment coming into these systems over time. In terms of the Rio Santa Cruz, so much of the water is just coming from this one lake, this single source. As I mentioned, there are little tributaries coming from the side, but they're just nothing compared to what's coming from that single point source. Exactly what's happening under the glaciers is hard to say. If I just go back to that picture, hold on. Yeah. So what we see today is basically an ice sheet, right? Just to the left of where the picture cuts out. So most of the source area is actually either heavily vegetated today or it's completely under ice. And they're going to be big changes through time. Like as this ice sheet grows and advances out to the edge of the lake, I'm sure there's just a tremendous amount of sediment it's going to mobilize and like suddenly release into the system. So I mean, these terraces are huge. You can, yeah, if you go, can't really see in my picture, but if you go to Google Earth and just zoom in, you'll see how big they are. I don't have any good terrace pictures from Patagonia because they're too big. I have a picture of one person on a terrace and all you see is a flat surface as far as the eye can go. You nearly need to see like from a satellite perspective, the different terrace levels because they're massive. So I think, yeah, I mean, I think all these processes are contributing to these massive variations in sediment supply to that system with these glacial advances and retreats, together with all the other hill slope processes that accompany it.
We still have questions coming in, so as long as you're happy to answer. So the next one is from Philip Johnson. In coastal regions, sea level change seem to control incision and aggradation. Is sea level change attenuated in these upstream settings?
You mean its effects? Yeah, I guess its effects on the alluvial channels. I'm sure it will depend on how much forcing you have versus how much sea level. I mean, yeah, for sure. If you have a drop in sea level, it's not just the change in sea level, but the slope of the channel offshore. So if you drop sea level in a way that suddenly exposes a continental margin, right, this can cause a big wave of incision to go upstream. If what you see offshore is just a continuation of the same slope that you had onshore, variations in sea level won't affect that system much at all. So it will depend on your offshore geometry. But of course, also, yeah, what is happening upstream if you have massive changes in water and sediment supply, that should still cause changes in your system. And that's what we see at a lot of field sites. So we do see these terraces forming and they're preserved. So.
Okay, there's still questions. Benjamin Kempfort says, amazing talk. The theoretical models focused on fluvial channels. What is the role of hill slope channel interactions in buffering or enhancing the climate signals?
Yeah, that's a great question to probe with more models, I suppose, of those hill slope processes. I mean, it's kind of, yeah, I don't want to seem like I'm giving a lame answer, but yeah, I think to really understand what is coming into our system, you need to understand the complexity of what's happening on the hill slope. So there's just no question about that. I think what would be very cool is if it'd be possible to take Andy's modeling and couple that with something that is more advanced, right? That is specifically modeling those processes. And, you know, I think, Rebecca, you were either asking a question directly or one from the chat. Also mentioning that, you know, what's happening on the hill slopes is very important, complex, and it's nearly something that we need to model separately. So, yeah.
If I may, I do have a question myself. A couple, actually. One, I didn't pick up, but and maybe you touched on this. What do you expect of the combined effects of these different frequency magnitudes of when you evaluate or measure these signals at the outlet? So say you have incision and aggradation signals all bundled up together, and you're just grabbing a sand sample at the outlet of these systems. What do you think will they will record the most, since it's towards the end and you have different effects along the stream channel?
Yeah. I think, yeah, maybe one of the takeaways is that if your forcing is dominated by variations in sediment supply, those are relatively easy to absorb along the channel if you have high frequency variations. So if you're forcing the system, you know, just with variations in sediment supply, it's going to be hard to see that downstream, far downstream. If you're forcing the system with variations in water discharge, that's different, right? Because this is where you get nearly a one-to-one response. As soon as you increase your water discharge, you have capacity to transport sediment. And even if you're only increasing it a little bit in the source area, you can pick up more sediment from the channel itself. So those are the kinds of forcings that we'd expect to see recorded in much higher resolution. Your other question, so what happens if we have, you know, everything I showed you was a single forcing frequencies. Obviously, what we have is, you know, different forcing frequencies that are superimposed upon one another. Yeah, I think that'd be very interesting to actually see what happens with the sediment discharge at the outlet, and under what conditions you can still capture the high frequencies together with the lower frequencies. I think it's really cool to see in Mitch's field site that, you know, essentially he would have one big old fan lobe that seemed to have subsets of ages that were then recording higher frequency forcing. So it's nearly like you get kind of one sublobe forming, then a little bit of an impetus gets another sublobe, but then a big change gets you to another mega fan lobe, right? If that makes sense. So you get little variations that can be recorded geomorphically before you then reset the system. And I haven't even looked in any detail of what happens farther downstream at the sinks, but yeah, interesting question.
Thanks a lot for the talk. I think this is the end of the questions. If anyone wants to ask a question, this is your last chance. Otherwise, thanks again. That was a very exciting talk, and it will be uploaded on YouTube in a bit. And otherwise, see you all next week for Harrison Gray's talk about fault scarp and sediment fluxes. Thanks again, Taylor, and see you all next week.
Yeah, thank you.